Hello, in this video we are going to solve for the flow around the slider bearing.
So first of all, let's draw the configuration of this slider bearing flow. So we do have a wall at the bottom, and this wall is supports a fluid. We have a slider bearing here, which is slightly inclined. And of course, in between the wall and the slider bearing, we do have a fluid. Okay, so this is our fluid. And whichever way we want to look at it, either the slider moves or this is this wall here that moves. So what in this configuration, what we're going to do is consider that this is this wall here that moves at a velocity capital U. Okay. So let's just define a few quantities here to characterize our system. So here is the axis for my referential frame. So this is EY, this is EX, and so this is going to be essentially our zero, the center of our referential. That distance here at the entrance of the slider bearing is called D1. I'm going to call this one D2. And well, at any point here, the height of fluid is going to be called H. And so I can write down that H, and I'm going to define also the length of the slider bearing. Here I need to define this length to be capital L. And so based on this, I can define the height of fluid. And the height of fluid is H of X. It's a function of X, and it's going to be at the entrance D1 plus X times, well, the slope here. So that's going to be D2 minus D1 over capital L of X. And that gives me the slider bearing, the height of fluid under the slider. And what we're going to do is we're going to define this quantity to be H prime, okay? And we are going to solve for the flow in this configuration for the absolute value of H prime to be small compared to 1, which means that effectively this slider is slightly inclined, only slightly. Okay, so this is a two-dimensional flow, so we can make the two-dimensional ansatz that the velocity of the fluid u is u as a function of x and y in the direction ex plus a component in the y direction, which I call v of x and y in ey. Once again, so we've made that approximation. The second approximation that we're going to make here is that we're going to consider that our flow is a low Reynolds number flow. So in the context of these low Reynolds number flows, what we have to write is the Stokes equation. That's going to be our starting point, Stokes equation. And that Stokes equation, I'm going to write it down in component forms so that we can directly plug these u's and these v's in there. That Stokes equation writes mu, that's going to be d2u by dx squared plus d2u by dy squared. So that's our viscous forces, and they're equal to the pressure gradient, dp dx. And similarly, I've got d2v by dx2 plus d2v over dy2, which is equal to dp by dy. Okay, and as it is customary, we complement these equations with the incompressibility constraints. Which reads that du by dx plus dv by dy equals 0. And that's going to be our starting point, our starting equations for this problem. So I'm going to label this one 1, 2, and 3 because we're going to go back to them in the immediate future. And before trying to solve for these equations, there's two more steps that we need to do. We forgot to write the boundary conditions. So the boundary conditions have to be specified at the beginning of each problem, because this is, on these boundary conditions, using these boundary conditions that these equations have to be solved. So at y equals 0, we're on the bottom wall, so y equals 0, the velocity of the fluid has to be the same as the velocity of the wall, okay? So this is our no-slip boundary condition, so that's uex. And the second one is that y equals h, and remember that h is a function of x, so that's going to be a non-trivial boundary condition to impose. Then the velocity has to be the same as the velocity of the slider, which is 0. Remember that we are considering that this is this bottom wall that is moving and not the slider. Okay, so first step in the solution to find the solution of the system is to non-dimensionalize it. So we are going to proceed to the non-dimensionalization. And to do this, let's introduce some scaling quantities for the directions and the velocities, for instance. So first of all, let me look at the coordinate y. This quantity, this is the height here. This is in that vertical direction. There is an obvious way of rescaling y, or of non-dimensionalizing y. It is to do it with the height of fluid. There are several heights that we can use. We can use d1, d2, or any combinations of them. They can be used interchangeably. What I am going to use here is use the average distance, because this is just a linear slope. So I'm going to use the average distance. So I'm going to non-dimensionalize y by h bar, where h bar is d1 plus d2 over 2 y star. Okay. And well, similarly, because I've introduced this, I can also write d1 star, which will be d1 over h bar, and d2 star, which will be d2 over h bar, in a similar fashion. So the start quantity that relates to distances in the y direction are going to be always non-dimensionalized using h bar. Okay, the second quantity that we want to non-dimensionalize is x. So that's a little bit more complicated, because we can decide to non-dimensionalize x using L, which would work. But this is not going to be interesting for us because of two reasons. First of all, L doesn't tell us anything about the physics in this problem. We can have a very long slider, but ever so slightly tilted, that it pretty much behaves like it's a one-dimensional flow, because the domain is nearly rectangular. But similarly, we can have a very short L and have a slider that would be extremely tilted, and therefore have a very two-dimensional flow, not very one-dimensional, because that domain would no longer be rectangular, but would have a very sharp upper wall. And vice versa. So this L, this quantity L, first of all, does not carry any strong physical indication on the flow. The second reason is, well, this is part of lubrication flows. These flows are nearly two-dimensional, or nearly one-dimensional, but they do contain a slight two-dimensionality. And to make this two-dimensionality appear in the calculation, or rather to preserve it, it's better to keep a small parameter here, or make a small parameter appear when we proceed to the non-dimensionalization. And this small parameter here that we have in this problem, well, it's actually this one. It's h prime. And this h prime quantify how tilted the slider is, right? H prime being small means that this slider is nearly horizontal. Furthermore, what h prime is dh, which is a y quantity divided by dx. And there we get our x appear in the process. So h prime being dy by dx, in a matter of speaking, we want to have 1 over h prime appear in our non-dimensionalization to get something that's homogeneous to x. So we're going to have this h prime in the denominator here. But remember, if we do this, then this h prime is h by dx, so it's a y over an x. That means that this 1 over h prime is an x over a y. So we need to cancel this y in the denominator, and we do this by multiplying by h bar, right? And that would help us, that would provide us a non-dimensionalization for x ultimately. Okay, so that gives us, and remember here that, remember just one thing, that h prime in absolute value is a small quantity. So that's going to play in introducing our slight two-dimensionality to the flow. Then we can also non-dimensionalize the velocity. So u, very trivially, we have a scale for the velocity in the x direction, which is capital U. So we're going to use it. So that's going to be capital U times u star. For v at this stage, we know nothing. So for v, I'm going to introduce this capital V. And I'm going to work on capital V to determine it. Okay. And last but not least, well, there's another problem here, is that we have the pressure, and the pressure is always bothersome in these fluid dynamics problems. So I'm going to just non-dimensionalize the pressure by capital P, and again, this is going to be determined. Okay, so this is our non-dimensionalization. Okay, so now that we have our non-dimensional quantities here, we can start working on determining V and P and simplifying this set of equations. So let's just start off by trying to determine V, and there's a very easy way to do this, which is to look at equation 3. It involves U, X, Y, and V. U, X, and Y have a clearly defined non-dimensionalization, so that will help us determine the scale for V. So let's just inject all this in 3. And so what we get is U H prime over H bar du star by dx star plus V over H bar dv star over dy star equals 0. So I can multiply everything by h bar, and by doing so I get u h prime du star by dx star plus v dv star by dy star equals 0. And if I want to preserve the two-dimensionality of the flow within the incompressibility constraint, then I have these two scales to agree. So in other words, that imposes that V equals U H prime. In other words, that the velocity in the vertical direction V has to be small compared to the velocity in the horizontal direction. Okay, so that determines V. Now let's have a look at what we can do for P. And well, P appears in equation 1 and 2, so let's just inject our non-dimensionalization into equations 1 and 2. So first of all, in equation 1, what we get is mu u h prime squared over h bar squared d2u star over dx star squared plus mu u over h bar squared d2u star over dy star squared equals, and I've got the pressure, so p h prime over h bar dp over dx star. And well, of course I can multiply everything by h bar squared divided by mu u. That's essentially going to simplify the prefactor here. And by doing this, I'm getting an h prime squared here. So h prime squared du star over dx star squared plus nothing appearing here. So I've got d2u star by dy star squared. And on the right hand side here, I've got the pressure appearing with p h bar h prime over mu u dp star over dx star. Okay, so that is my first equation. Then I can look at the second equation, and well, this is going to be essentially the same, with the only difference that there will be an extra h prime coming out of the fact that we have v instead of u here. So that's mu u h prime cubed over h bar squared d2v star over dx star squared plus mu u h prime over h bar squared d2u star, it's a v, d2v star over dy star squared equals, and on the right hand side we don't have a dp by dx but dp by dy, so this h prime goes away and we have p over h bar dp star over dy star. And in a similar fashion to the way we treated equation 1, I'm going to multiply all this by h bar squared over mu u, and I get h prime cubed d2v star by dx star squared plus h prime d2v star over dy star squared. And on the right hand side I'm getting p h bar over mu u dp star over dy star. Okay, so these equations are written now in non-dimensional form, and I'm going to just label them 4 and 5 because we are going to get back to them in a second. So first of all, if I look at this equation, on the left hand side what I have are two terms related to diffusion. This term has an h prime squared in front of it, which means that it's small squared, and this one as just a unit prefactor. So this guy is going to be h prime squared smaller than this guy. In other words, I might as well just neglect it. In a similar fashion, if I look at this equation, equation 5, I'm getting the same thing. This guy is h prime squared smaller than this guy, and so I might as well also just discard it. And I've got a balance for equation 4 and 5 between only one term in the diffusion and the pressure gradient. So equation 4, if I want to preserve this balance, equation 4 tells me that ph bar h prime over mu u equals 1. Okay, so these two terms have the same magnitude, order of magnitude, and that tells me essentially that p has to be equal to mu u over h bar h prime. So that's from equation 4, and a similar reasoning applied to equation 5 tells me that this time I'm going to have an h prime in the numerator here. So p has to be mu u h prime over h bar. Okay, so I've got two different scalings depending on which equation I look at, but these equations have to be solved simultaneously. So I can either say that p is small, and I'm going to get this h prime here, or I can say p is large, and I'm getting this 1 over h prime here, right? This is the large one. And based on the two, if I say p is small, then I'm not including this in the scale of p, because something large has been neglected. But if I say p is large, well, the small p is still included because, well, you know, it's contained in the large one. So, in other words, that gives me with one choice to include both possibilities, which is to say that p is large. So p goes like mu u over h prime h bar. Okay? And so now we've determined v, we've determined p. We can just proceed to write down, to recapitulate on our non-dimensionalization and to write down the equations in their non-dimensional form. So let's just summarize on this. So we've written that x equals h bar over h prime x star, y equals h bar y star. We've written that u equals capital U star, v equals u h prime u star, v star, sorry, v star. And we've just introduced the scaling quantities for p, which are mu u over h bar h prime time p star. Okay, and this is so what that tells us is that the pressure is large and the velocity in the y direction is small compared to the velocity in the x direction. And we can also introduce like a scaling quantity for if we wanted for h. We can write down that h is h bar h star, and therefore that h star equals d1 over h bar. I'm dividing already by h bar, plus this is h prime, remember, so plus h prime over h bar, and I've got x, and so x, if I replace by x star h prime over, h bar over h prime, I've got x star here, which means that h star is d1 star, as I mentioned, you know, it's a quantity in the y direction. I'm dividing by h bar, so that's essentially the non-dimensional quantity in that direction. These groups simplify, and so I'm getting just x star here. So an interesting consequence of this is that dh star by dx star equals 1. And that's how we non-dimensionalize our quantities, by a distance that is such that the slope of h star as a function of x star is units in this non-dimensional quantities. So this is our summary for the non-dimensionalization, and I can also introduce the non-dimensional equations. These non-dimensional equations, if I take again 4, so 4 is the one for which we have used the non-dimensionalization. So that'll give us d2 u star by dy star squared equals dp star by dx star. Then 5 is not going to give us something very nice. So 5 is giving us h prime, that's our left hand side, d2 v star by dy star squared equals, okay, and on this, if I replace, the mu u go away, the h bar goes away, and I'm getting 1 over h prime dp star by dy star. What we can see from this is that this term is small, this term is large, and so if I multiply everything by h prime, I get h prime squared here, which I can neglect and just keep this term. In other words, this equation tells me that there is no pressure variation in the vertical direction. And the last equation that we have is the continuity equation, or the impressibility constraint, for which we've got both terms still present. So du star by dx star plus dv star by dy star equals 0. And this is our system. And the boundary conditions at y star equals 0, what we get is that u star equals 1. I'm not dimensionalizing by u. And v star equals 0, and at y star equals h star, that's our second boundary condition, we get u star equals v star equals 0. And this is the whole problem that we have to solve in these non-dimensional quantities. So before solving these equations, we have to label them because we're going to get back to them quite a lot, and I'm going to have to turn the page. So let's just label this one 6, this one 7, which is just dp by dy equals 0, and this one 8. Okay. So first of all, we can very quickly assess the usefulness of equation 7. Equation 7 is just there to tell us that there is no variation of the pressure in the y direction, and therefore that P is a function of x star only. Okay, so that's a very quick one. And based on this, we can integrate equation 6 with respect to y. So equation 6 then yields that the velocity in the x direction u star has to be equal to 1/2 of dp star by dx star y star squared plus a constant of integration that may depend on x star, y star, plus another constant of integration k2 that may depend on x star. So that's what equation 6 gives us. So now we're going to apply the boundary conditions, and for u, right? And then we have these two boundary conditions. So first of all, let's write down the boundary conditions. So first of all, at y equals 0, y star equals 0, we have to have u star equals 1. And that very directly gives us that k2 equals 1. Okay, and I'm going to turn the page to solve for the next boundary condition. So the second boundary condition is at y star equals h star, then we have that u star has to be equal to 0. And what that gives us is, we're going to replace all this by h's, so that's 1/2 of dp star by dx star h star squared plus k1 h star plus 1 equals 0, or in other words, that gives us that k1 equals minus 1 over h star minus 1/2 of dp star dx star h star. Okay, and so I can plug this back into all these unknowns, k1 and k2, and bear in mind that k1 does depend on x, because h star depends on x, right? Remember that we wrote down that h star was a linear function of x, and similarly we haven't determined what dp star by dx is, but this is something that we'll determine soon, and it depends on x. So I can replace the constants of integration in the expression for the velocity in the u direction, and by doing so I'm getting a solution which is 1/2 of dp star by dx star. I'm going to have y star squared minus h star y star plus 1 minus y star over h star. And that's my velocity in the x direction. But it's not entirely determined because we do not know at this stage what dp star by dx star is, right? Remember that the pressure is an unknown in this problem, and needs to be determined because it might be doing some unpredictable fancy things under our slider. So, well, how do we go about and determine the pressure? So far we've used equation 6, we've used equation 7, we've used the boundary conditions for u, but we haven't used equation 8 and the boundary conditions on v. So let's use these last remaining pieces of information to try and determine the flow. So we can determine from 8, we can determine v by integrating du by dx with respect to y. And so let's just do this. Let's equation 8, yeah, it's equation 8. So 8 gives us that dv star by dy star equals minus du star by dx star. And in other words, I can integrate this with respect to with respect to y between 0 and y star. 0 will give me v star at y equals 0, which is 0, so that's my boundary condition, which is very useful. And so I've got v star at y star minus v star at 0, so that is to say v star, equals minus 0, the integral from 0 to y star of du by dx. So du by dx is 1/2 of d2p star by dx star squared, y star squared minus h star y star, minus 1/2 of dp star by dx star, dh star by dx star y star, plus y star over h star squared, dh star by dx star, and the whole of this integrated with respect to y star. Okay, so that gives us conveniently the zero boundary of integration is always going to give us 0, so I'm just going to focus on the upper bound when I'm integrating. And so what that gives us is minus 1/6 of d2p star by dx star squared y star cubed plus 1/4 of d2p star by dx star squared h star y star squared. So that is my first terms here. Then I've got plus 1/4 dp star by dx star, dh star dx star y star squared, minus 1/2h star squared dh star by dx star y star squared. And I think that's it. That sounds like it's correct. So now we've written down v. Again, there's some dp dx's and dp dx squared, and there's even dh by dx in there. None of this is very convenient, but we haven't used all our all the information that we have at hand. We haven't imposed this boundary condition at y star equals h star, v star equals 0. So we're going to impose this. So boundary condition. So y star equals 0, we have v star equals 0. Okay, so that gives us that minus 1/6 d2p star by dx star squared of h star cubed plus 1/4 d2p star by dx star squared h star cubed plus 1/4 dp star by dx star dh star by dx star h star squared minus 1/2 dh star by dx star equals 0. This is our boundary condition here. We can simplify it a little bit, and we can just isolate this guy and then combine these two. So if I do this, what I get is 1/2 of dh star by dx star equals 1/12 of d2p star by dx star squared h star cubed plus 1/4 of dp star by dx star dh star by dx star h star squared. And while we're there, we can pause for a little second, and in fact what we can see is that on the right hand side, these terms are coming out of the differentiation with respect to x of dp dx times h squared. And, h cubed, sorry. And so, if we multiply everything by 12 and then integrate and then factorize the right hand side by the d by dx star, then what we get is 6 dh star by dx star equals, so here I'm gonna factorize by this derivative. So I multiplied everything by 12, so this is 1, and I said this would be dp star by dx star h star cubed. So let's just have a look at this. So if I differentiate inside here, I get d2p star by dx squared h cubed. This is this term here. And then I get 3 h star squared dp dx star, which is this term. So this is correct. And we end up with this equation. Okay, so this equation is a particular equation in fluid dynamics, not necessarily under that form, but an equation that relates the height of fluid with the pressure, with the pressure gradient in the orthogonal direction. This equation is a typical step that one takes to solve for various lubrication flows or various free surface flows, and it's called the Reynolds equation. So now let's have a look at how to solve the Reynolds equation. So first of all, well, we can just integrate everything with respect to x. So if I do this, and I'll just take this to the left hand side because I'm going to work with this term rather than this term. So that gives us that dp star by dx star times h star cubed equals, so integrating this with respect to x star will give us 6h star plus a constant of integration, and just to make the calculation simpler I'm going to keep the 6 in there, so that's plus 6k3. I think that I was at 3 in terms of my constants of integration. k1, k2 here, so I must be at 3. So that's 6k3. So the next step I can just divide everything by h star cubed, so that's dp star by dx star equals 6 over h star squared plus 6k3 over h star cubed. And you can see here that we have expressed dp star over dx star, right? So one could say, oh, I'll get back to my velocity in the u direction, and I plug this in, and I've got the full definition, the full determination of the velocity. But that is not correct, because there is this constant of integration, k3, that comes out from the calculation. We need to determine this. So you might think that we've opened Pandora's box here, because every time that we use a new hypothesis, we end up getting one new piece of information, but there's another piece of information that's still missing. That is not entirely wrong, but there is another thing that we can do here to solve for this flow, and particularly to determine K3. So if you go back, when we're just running out of hypotheses like this, we need to go back to the problem at hand. So what we have here is a slider bearing, and we've solved for U, we've solved for V, we've solved for the pressure, and there's this K3 constant of integration that's lurking around and preventing us from fully determining the flow. It appears in dP by dx, the pressure in the the gradient of pressure in the x direction. And bear in mind that the pressure does not depend on the vertical direction. We've determined from equation 7 that dP star by dy star was equal to 0. So effectively, what we need to determine, what we need to find is an extra condition for the pressure that would allow us to determine that K3. luckily, we can provide such a condition because, well, to the left of the slider bearing, there is no influence of the slider. To the right, it's the same thing. In particular, when it comes to the pressure here has to be equal to the pressure there. It doesn't vary with y, and therefore the pressure here has to be equal to there. This is the atmospheric pressure. So what we should have is the pressure at x equals 0 has to be equal to the pressure at x equals L. And so we're going to integrate this dp by dx between 0 and L. And I'm going to write down that in non-dimensional quantities. So I'm going to put L star, for instance, which is going to be L times times h bar over h prime. But I'm not going to bother carrying these quantities around. So by integrating this between 0, x equals 0 and x equals L, what we have is P star at L star minus P star at 0. Okay, and that's going to be equal to integrating this, okay, and dp by dx is dp by dh by dx, and dh by dx is 1 in non-dimensional quantity. Remember that we wrote this down here, dh by dx was 1. So instead of integrating this equation with respect to x, we can just integrate it with respect to h without making a mistake here. So that will give us here, integrating with respect to h, minus 6 over h star. That has to be taken from x star equals 0 to x star equals L star. And I've got this second equation here, the second term here, which gives me minus 3k3 over h star squared. And that's also going to be taken between x star equals 0 and x star equals L star. Okay, so x star equals 0 means h star equals d1 star. Okay, so you remember d1 at x star equals 0, h is d1 star, h star is d1 star, and at x star equals L star, h star is d2 star. Okay, so that's h star equals d2 star, and that's going to be the same for these guys. Okay. And furthermore, as we said, the pressure on the left of the slider bearing has to be equal to the pressure to the right of the slider bearing at the surface. Therefore, because dp star by dy star equals 0, it's got to be everywhere at these x coordinates. And so p star of L star minus p star 0 it has to be equal to 0. Okay, so because this is 0, we can recast this equation and essentially write down that, well, I'm just going to use these on the left hand side. So that's 6 divided by d2 star minus 6 divided by d1 star, and that's going to be equal to the right hand side to 3k3 over d1 star squared minus 3k3 over d2 star squared. Okay? And well, d1 star, d2 star are known quantities. k3, I do not know what it is, but it's the only unknown quantity here, so I can directly solve for k3 and write down that k3 then becomes twice times d1 star squared d2 star squared over d2 star squared minus d1 star squared times d1 star minus d2 star over d1 star d2 star. And therefore, I can simplify this and write down that K3 is 2d1 star d2 star. And I'm going to have a minus sign here divided by d1 star plus d2 star. Okay, so that's our K3. As a consequence of determining this K3 here, we can write down now the pressure gradient dP star by dx star as, where do I have it last? I have it there. So that can be written as 6 over h star squared, and I've got plus 6k3, so that's going to be minus 12 d1 star d2 star over d1 star plus d2 star h star cubed. Okay, so that is our dP by dx. And then because we've determined dP star by dx star this way, we can get back to U star and writing down the full expression now entirely determined of U star. So U star is 1/2 of dP by dx. Okay, so I can divide all this by 2. So that's going to be 3 over h star squared minus 6d1 star d2 star over d1 star plus d2 star h star cubed times y star squared minus h star y star plus 1 minus h star over h star. Okay, and this is our full determination for the velocity in the x direction, where you can see that it depends on y explicitly here, and it depends on x implicitly through these h star quantities. Okay, so these are implicit dependences on x star. Remember that h star is d1 star plus x star. So I've only decided to express here, this is already a pretty lengthy video, the velocity in the x component. This is a dominant velocity, okay? The velocity in the, sorry, I should have looked at here. The velocity in the y direction is small compared to it. It's got a prefactor h prime, so I didn't want to solve for this as a priority. And you can also determine the pressure and do some further reasoning on the solution. But I would like to stop there with this milestone result in this solution for the slider bearing flow.
In this video, we've solved for the slider bearing flow. This is a quasi one-dimensional flow that carries a little bit of a two-dimensionality. This is a type of flow known as a lubrication flow. We've used the lubrication hypothesis or asymptotics on the solution to try and determine the dominant terms, and from these we simplify the equations and solve for a fully two-dimensional resolution of this flow. This concludes this video on the slider bearing flow.